Assalamu alaikum. So in the previous lectures we discussed about the symmetrical faults and we have concluded this type of topic that symmetrical faults have been completed. Now coming to this unsymmetrical fault, it is somewhat complicated because you can see there is no balance current. So unsymmetrical fault is that fault which is not symmetrical. We can see that it is not balanced fault. Balance means when IA plus IB plus IC is equal to 0, that means it's a balanced system. But if IA plus IB plus IC is not equal to 0, it is not a balanced system. We can say that we have some neutral current in that case. When the system is not balanced, we have neutral current will be non-zero. Usually in Y connection, in delta connection, this will always hold. And what we mean by balance of the system, it means when the magnitude of IA and IB and IC are equal and they are displaced by an angle of 120 degrees. So any equation, any condition that goes against this, that means which is not following the magnitude or angle criteria, we can say that the system is unbalanced, or if the fault takes place in such a manner which results in this magnitude wise different currents and angle wise different angles. So in that case, that type of fault is an unsymmetrical fault. Sometimes you may see the magnitude of currents are same but angles are not same, or angles are not same and equal to 120 degrees. Sometimes you may see that magnitude of the current is same, angle is also same, but that angle is not 120 degrees. That's also unbalanced system. We can say that angle may be 60 degree, that angle may be 90 degree, that angle may be 100 degree. So whatever be the case, it should be magnitude same and 120 degree. Otherwise, if this is violated, this condition is violated, it is unbalanced. So I have summarized it. It is not actually, these equations are not totally complete. It may miss something, but in general, we can keep this in mind. If the magnitude is same of all the currents and angle between different currents are 120 degree, it is balanced. And if it's other way around, that means if any one of these is violated, we say that the system is unbalanced. So I have tried to write down different conditions which result in the unsymmetrical faults. So you can try on your own, but please keep in mind that even if magnitude is same, angle is same, but different from 120 degree, it is still unsymmetrical fault. So some examples of the unsymmetrical fault. In the previous symmetrical fault, we have usually two examples. That is the three-phase fault without involving the ground, or three-phase fault involving the ground. In both the cases where the three-phase fault is involving the ground or not involving the ground, you will see that the presence of the ground has no effect on the fault, because in that case the three-phase fault is itself symmetrical fault, which results In to be equal to 0. That means ground effect will not have any contribution. So here we have three types of fault in general. That is LG fault, that is phase to ground fault, or sometimes single line to ground fault. For example, if phase A to ground are connected or get in touch with each other, phase B to ground, phase C to ground, such type of fault are also known as the earth faults because it involves the earth or ground. So phase to phase fault, for example, AB fault, BC fault, or CA fault, such kind of fault in this field are known as overcurrent fault, but not in the theoretical part. Theoretical part, they are known as phase to phase fault or line to line fault. The third one is line to line ground fault. It is ABG, ACG, BCG. It also involves the ground. It is also included in the earth fault. It's also known as earth fault in the field, uh, in the field itself. So it also involves the ground. It is known as line to line fault or phase to ground fault. Double line to ground fault. So before going into the more explanation of the unsymmetrical fault, we'll first discuss the operator A. Operator A, its actual value is 1 angle 120 degree, its magnitude is 1, and it is at an angle of 120 degree from this reference. So when we take it into rectangular form, it is 1 cos of 120 degree plus j 1 sine of 120 degree. It comes out to be minus 0.5 plus j root 3 by 2. When it can be shown on the complex plane, it will be like this. This is its magnitude, which is equal to 1, and this is angle with respect to this reference. So this is the phasor A. A square is the multiplication of A into A. It can be written as 1 angle 120 degree into 1 angle 120 degree, which comes out to be in complex. We can simply multiply the magnitude and add the angles. Adding the angle, we get 240 degrees. So I can write it in rectangular form, that is cos 240 degree plus j sine 240 degree. It comes out to be minus j minus 0.5 minus j root 3 by 2. It can be shown like this. From this to this, it seems that this is the same phasor, but it is rotated from this position to this position by 120 degree. You can see it from here, because this one is 120 degree and this one is again 120 degree. From this position, total is 240 degree. We can say that by multiplying this operator A to any phasor, let us say this is the initial phasor, it gets rotated by 120 degree without changing the magnitude. We'll come to know this. Similarly, A cube is the A into A into A. It is 1 angle 120 degree into 1 angle 120 degree into 1 angle 120 degree. That is 1 angle 360 degrees. That can be written as 1 angle 0, or it is equal to 1. So it can be shown like this. It is exactly in phase with the reference. Its angle will be 0 or 360 degree. So we can see that A cube will be equal to 1. Similarly, A raised power 4 can be written as A raised power 3 into A, where A raised power 3 is 1, and it comes out to be equal to A. Similarly, you can go for higher powers like A raised power 5. A raised power 5 will be A square, and then A raised power 6 will be again equal to 1, because it will be A cube into A cube. So for any value of this, any power of the A, you can calculate, and you will see that it will always come either 1, A, or A square. 1 will be when raised power will be the multiple of 3. A will be when raised power will be multiple of 3 plus 1. Similarly, 2 will be, that is power of 2. A square will be when the power will be multiple of 3 plus 2. So here we can write this again, A cube. This A cube is equal to 1. I write it here again. A cube is equal to 1. That means A cube minus 1 is equal to 0. I can expand this. This is the formula of this. A minus 1 into A square plus A plus 1 is equal to 0. So when the multiplication of two factors is 0, it means either both of them are 0, either one of them are 0. So we can write either A minus 1 is 0, either A minus 1 is 0, but A is equal to 1 angle, this to 1 angle to 120 degrees, so it cannot be equal to 0. So that means this is not a solution of this. It means A square plus A plus 1 is equal to 0. You can see it from here. This A square is this phasor having the magnitude of 1. A is this phasor having the magnitude of 1, and 1 is this having a magnitude of 1. When they are, you can see it when you form a triangle, you'll see that their value will be equal to 0. So you have to keep in mind this relation. Is very important. We will be using this quite frequently. Now coming back to the, I will explain a bit more regarding this operator. When this operator A is multiplied to any phasor, it rotates the phasor by 120 degree in anti-clockwise direction without affecting the magnitude. For example, if this is a phasor A whose angle is theta with respect to this reference, when it is multiplied by A, it will be shifted in anti-clockwise direction by 120 degrees without changing the magnitude. This magnitude will be same, but you will see now this angle from this point to this point will be equal to theta plus 120 degree. Now phasor A has a magnitude A and angle theta with respect to reference, that is this one. So when this is multiplied by A, we get A times A. This phasor is rotated by 120 degrees anti-clockwise from its initial position without affecting the magnitude. This I have explained. When A is multiplied by A square, we get A square into A, that is shown here. This phasor is rotated by 240 degree anti-clockwise direction. You can see from here to here we have, because this is 120 degree, this is 240 degree, and this is theta. So it will be, this phasor will be rotated by 240 degree. That means total angle from this point to this point will be equal to 240 plus theta. So anti-clockwise from the initial position without affecting its magnitude. Magnitude will be same. Now the angle of the phasor will be theta plus 120 degree with respect to reference. That I have explained here. That means this angle from this reference to this point will be theta plus 240 degree. Total angle that has displaced, actual displacement of this from this point will be 240 degree. Similarly, the angle of this will be 120 plus theta. So I hope this is actually the operator A, what it does when it is multiplied by the uh, multiplied by when it's multiplied to a phasor. When a cube is multiplied to the phasor, it will not affect magnitude as well as it will not affect the angle, because the rotation is 360 degree. It rotates it by 360 and it comes to its original position. So that these two are important and others are not important. Now coming to the symmetrical component, what are symmetrical components and why are they important? In case of symmetrical faults, what we did, we did the per phase analysis, because in that case we have all the currents are same, and they are displaced by 120 degrees, so we can use the per phase basis and try to solve the circuit, and then we can extend that to the three-phase circuit. But here, since the system is not balanced, so we cannot use the earlier technique per phase basis. Actually, we have to go for per phase basis, but first we have to calculate the symmetrical component. So what we do in this unsymmetrical fault, we divide the unsymmetrical current or voltage into three different symmetrical components, and these are known as symmetrical components because they are itself balanced. So this was given by the Fortis, and the theorem is known as the Fortis theorem. According to this theorem, the three unbalanced vectors, that is VA, VB and VC, can be replaced by a set of three balanced system of vectors. The balanced system three vectors is one in which the vectors are equal. The three symmetrical components vectors replacing VA, VB, R. So what we do here, we replace the unsymmetrical components by a three balanced system of vectors. The first one are known as positive sequence components, the second one are known as negative sequence components, the third one zero sequence component. I will explain a bit about these components first. What are these? Positive sequence components which has three vectors of equal magnitude but displaced by 120 degrees from each other and has the same phase sequence of that of the original vectors. Because you can see we'll be deriving them from the original vectors, three phase unbalanced original vectors of voltage or current. They have their own sequence, and based on these sequence, if the three balanced system vectors have the same sequence of the original vector, we say that these components are known as positive sequence components. Others are known as the second category is the negative sequence components, and these type of components are those which are derived from they are also derived from the three unbalanced vectors, and the sequence of them are opposed to that of the actual three-phase unbalanced vector. When the sequence is opposed, that's why they are known as negative sequence components. Now, zero sequence components which has the vector equal in magnitude and they are also in phase. They have these two have the equal magnitudes and 120 degree by they are displaced by 120 degree. They are balanced components, negative sequence, but they are not balanced. They are same, but they are in phase. Their angle with respect to each other is zero. They can be shown like this. Now let us say these are the actual vectors. You can see from here they are not balanced. This is VA, this is VB, and this is VC. When we go from VA, VB to VC, you can see the sequence is clockwise. The actual sequence of the actual voltages are clockwise. Now these are the positive sequence components. Positive means we have denoted by 1, VA1, VB1 and VC1. You can see the sequence of these vectors are same as that of this. So that's why they are known as positive sequence components, because their sequence and the sequence of the actual vectors are same. Similarly, for the negative sequence components, they are again displaced by 120 degrees and they have the same magnitude. Magnitude, that's VA1 is equal to magnitude of VA2, VB2 and VC2 are same here. Magnitude of VA1, VC1 and VB1 are also same, but they are not same. VA1 and VA2 are not same in magnitude, and also they are individually displaced from each other by 120 degree. Positive sequence component and negative sequence components are also individually displaced from each other by 120 degrees. Similarly, we have the third one, that is the zero sequence components, denoted by VA0, VB0, VC0. Again, they have the same magnitude, but they are in phase. They don't have a displacement of 120 degrees. So, so after this, The fourth suggested that VA can be represented the summation of all the three voltages, that is the positive sequence voltage of A, negative sequence voltage of B, and zero sequence voltage of A. Sorry, this is A. Similarly, VB can be represented by the positive sequence voltage of B, positive sequence voltage of, sorry, negative sequence voltage of B, and zero sequence voltage of C. Similarly, VC can be represented by positive sequence voltage of C, negative sequence voltage of C, and zero sequence voltage of C. Now you can see from here, from this, the angle difference between VC1 and VA1 is 120 degree. That means if we multiply this A by this VA by an operator A, it will come to VC. That means in that case, VC1 and A times VA1 will be same. Similarly, this VB1, if we multiply this A square to VA1, it will rotate to this by 140 degree and it will coincide with VB1. So I have written this here. VB1 can be represented by A square VA1. You can see it here. VB1 can be, because magnitude is the same, angle is different by 1 to 240 degree. When we multiply it by A square, it means it is 240 degrees are added to it, or it is rotated by 240 degrees, it will come over here. We can say that VB1 is equal to A square VA1. Similarly, VC1 can be equal to A into VA1. I have written that over here. VC1 is equal to A VA1. Again, VB1 is equal to A VA2, because this is rotated by 120 degree to this. It will coincide then with VB2. Similarly, if this is rotated to 40 degree, it will be coincident to VC2. That is, we can say it in equation VC2 is equal to A square VA2. So here I can replace this VB1, VB2, VC1, VC2, and this VB, you can see it from here, VA0, VB0, and VC0, they are equal. So I can replace this VB0, VC0 by VA0. Actually, I want to represent all these voltages VA, VB, VC in terms of only VA1, VA2, and VA0. So I will first write out VA0. This will be VA0. This will be VA1. That is this VA0, VA1, VA2. I have just shuffled the different terms over here. Then this VB0 is first. It is actually equal to VA0. This VB1 is equal to A square VA1. I replace this VB1 by A square VA1. Similarly, VB2 is equal to A times VA2. You can see it here. I have written A times VA2. Now C is equal to VC0 or VA0. So VC1 will be equal to VA0. VC1 here I have written over here. That is A VA1. And VC2 is equal to A square VA2. VC2 is equal to A square VA2. Now I can represent them in a matrix form. So this can be also a matrix by using particular basis. So this is here VA0, 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 because they are similar. This will be equal to VA1, 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 1, A square, A square. This is VA2, 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 1, A and A square. So I will write them in terms of this matrix. So here it is VA1, VA0, VA2. This will be 1, 1, 1 for this case. For this case, it will be 1 because VA1 and VA0 and VB2, VB0 are same. So this will be 1, and this then this A square, then this A, 1 A square A. Then for this it is 1, this A and A square. So this is in the matrix form. So here we since we know this, we can calculate this VA1. We can measure this rather, or we can simply calculate by using the circuit analysis the value of different voltages at any point, three-phase voltage by using the three-phase analysis. Now we need to calculate this. So to calculate this, we can say we can use the inverse of this, directly inverse of this, multiplied by this. We can get VA0, VA1, and VA0. There are one more process of doing that. I will add VA and A times VB and A square times VC. You can see that. Then give the value of VA in terms of their component sequence components. This will be VA0, VA1, and VA2. That's VA, this A, and then VB. VB is VA0. This whole is not equal to VB. From this point to this point is VB. This is VA0 A square VA1 plus A times VA2 to be equal to VB. A square into VA0 plus A VA1 plus A square VA2. This is actually VC. That is this. So here we can simply this VA0 A times VA0 and A square times VA naught. VA we will take out, and in the bracket this uh, 1 for this, and A for this term, A into VA naught, and A square into VA naught. So it comes 1 plus A square, and we know that it's equal to 0. Similarly, VA1 here we have 1. So for VA1 here, it is A square into A, it is A cube, and for VA1 here, it is A square into A cube. So it will be like this. Similarly, for VA2, you can see VA2 here will be 1. Here VA2, it will be A, and for this VA2, it will be A square. So this will also come out to be equal to 0. So in that case, this VA plus AVB plus A square VC, that is this term, will be equal to, this is 1 plus 1 plus 1, because A cube is equal to 1, is 3A1. From here we can get the value of VA1. VA1 will be equal to 1 by 3 VA plus AVB plus A square VC. Now if we simply add the three voltages, it is VA plus VB plus VC, and then we give the sequence voltages of VA, VB, VC. You can see this is VA plus VB plus VC. So this is VA naught, VA naught, VA naught is 3 VA naught. This is VA1, A square VA1, A VA1. So VA1 taken out will be 1 plus A square plus A. Similarly, VA2, this is actually VA2, not V2. VA2, that is 1, A VA2 and A square VA2, that's 1 plus A square. So these terms will cancel out and will be equal to 0. So this VA plus VB plus VC is equal to 3 times VA naught, or VA naught is equal to 1 by 3 VA plus VB plus VC. We can say that VA naught is the average of the three voltages, but phasor average, not the algebraic average. So this is, I have written over here, VA naught is equal to 1 by 3 VA plus VB plus VC. Similarly, we can calculate VA2, it will be equal to 1 by 3 VA plus A square VB plus A times VC, like we have calculated this VA1. So we have calculated the sequence voltage as well. We can represent them in terms of matrix also, that I have done over here. You can see it. This is the actual voltage which we have first calculated, VA, VB, VC, that's 1, 1, 1, 1 A square A, 1 A square, VA naught, VA1, and VA2. Similarly, currents can be represented in the same manner. And this is the sequence components in terms of actual voltage. This is the actual voltage in terms of the sequence components. So this sequence components, you can see this and this, they are actually inverse of each other. We have not calculated the inverse. It is very difficult because in calculator to calculate inverse of the complex number is very difficult. So I have used a different technique to calculate this, and then calculate the matrix. This matrix will definitely be inverse of this matrix. So this is VA naught, VA1, VA2. This, if we say this matrix to be A, this whole matrix including this 1 by 3 will be equal to A inverse. So this is VA naught IA, VA, VB, and VC. Similarly, IA naught, that is the sequence component of the currents in terms of the actual currents, will be, sorry, I have forgot to write the 1 by 3. Here it is 1 by 3, definitely. So this is how we can calculate the sequence voltage or currents from the actual voltages which are unbalanced. So we can calculate the complex power in terms of the symmetrical components. So we know that actually I have omitted the derivation. The derivation is given in the books. I will write down directly what is the actual formula. This is the complex power is 3 times VA naught IA naught star plus VA1 IA1 star plus VA2 IA2 star. So in terms of matrix, it can be written as a VA naught, VA1, VA2, IA naught, IA1, IA2 a whole star. So this is actually complex power P plus JQ. P will be equal to 3 times VA naught IA naught cos of theta naught. So this theta naught will be the current between the zero sequence voltage and zero sequence current. Similarly, 3 times VA1 IA1 cos of theta 1. Again, this angle will be the angle between this voltage and this current, plus 3 times VA2 IA2 cos of theta 2. You can refer to the different books. There the derivation is given in almost all the books. I omitted it because I thought it's not very important. You should know what is the form, how can we calculate the formula. They can be calculated from the individual components. You can see it from here, they are decoupled. You can see that the power of zero sequence components is dependent upon the zero sequence components of voltage and current. It is independent of the power. That means there is no term of positive sequence component in the zero sequence component of the power. So this was important in that case to show you the decoupledness of the system. That is very important, and that makes our system calculation very easy when we have three sequence components which are very important, independent and decoupled, and they don't have any mutual relation between each other. Now let us try to do one numerical and calculate it. We'll have the actual currents. We'll calculate the sequence current from the unbalanced currents. So the line currents in the amperes in phase A, B, and C respectively are, that's 500 plus J150. IB is 100 minus this J600. IC is minus 300 plus J600. We need to calculate this symmetrical currents. So the formula for symmetrical currents in the matrix form is given by like this. So from the first row, from this, that is first equation, that's IA naught will be equal to 1 by 3 IA1 plus IB, sorry, IA plus IB plus IC, that is the average of these three. It comes out to be equal to 100 plus J50, and in complex form, or we can say this was a rectangular form, this opposite form, it comes out to be 111.80 angle of 26.56. Similarly, IA1 will be equal to 1 by 3 IA plus A times this IB plus A square times IC, like this. So when we calculate it, it comes out to 546 plus 3.3 plus G165.46 amperes. So in polar form, it will be like this. Similarly, IA2 will be equal to this value, 160. You'll see that these okay. So this will be these three components, IA1, IA2, and IA3. Now we'll calculate other components, that is IB1, IB naught, IC naught, and IA naught. They will be same. They will be equal to having the same value, this and this. So IB1 will be equal to E square IA1. So there will be only a displacement of 240 degrees. So it will be 570 to 56.8 because the magnitude will remain the same. So this 256.8 is in third quadrant. It can be represented by the minus angle as well, that is 103. That is this 256.8 minus 360, it comes out with this value. Similarly, IB2 will be equal to 8 times IA2, it comes out with this value, 160.38. It will be, magnitude will be same, but angle will be different by 120 degrees. Similarly, IC1 and IC2, they can be simply multiplied by A and A square and and we get the actual value. You will see that IC1, IA1, and IB1, they will be the three currents which will be balanced. You can see IB1 is this, magnitude of 570 point this, IC1 is this 570.8, and IA1 also, IA1 that is 570.80. They have the same magnitude and angle will be different from each other by 120 degree. You can see it from here, IB1 and IC1. Where is IC1? That's this 136 point this, and IB1 is sorry, it's not this, IC1, that is 136.8, and this will be 240 degree difference of the angle. And IA1, you can see it from here, IA1 is 16.8, this is 16.8, there is 20 degree angle difference, and magnitude is the same. One important thing, and the other important thing is that you can see it from IB2. IB2 is 160, and its angle, we first see IA2. IA2 is 160, 155. You can see IA1 and what I mean to say is that, okay, IA1 and I'll go back to the actually, yes, this. Okay, this I can I have written here voltages and we have calculated currents. I will talk in terms of current. This IA1 and let us say IA2, we say that they are in phase. Here I have shown it, they are in phase, but it is not necessary always. They are in phase. They will have a different magnitude, as I have told earlier, these two, and they will have a different angle with respect to reference. Okay, please keep this in mind. But VA1, VC2 and VB2, they have the same magnitude, angle difference is 120 degrees. VA1, VC1 and VB2 have same magnitude, angle difference 120 degrees. Here VA1, VA2 and these, they will have a different magnitude and different angles with respect to the reference. You can see it from here. IA naught is 26.5, magnitude is 111 point this is 570, and this is this. You can see magnitude is different and angle also different from the reference, and their other components will be different from their respective components by 120 degrees. Such things are to be taken into consideration. So this was one numerical problem. Now one important thing is how to calculate the voltage of a neutron. Let us say we have a this star connected system. This is the source, this is the voltage, where both the neutrals are connected to ground. Here the neutral is connected to ground directly. This is known as solidly grounded system, when neutral is connected to ground directly without any impedance. Here it is solidly grounded, here it is grounded through impedance Zn. We know that this In will be equal to this current Ia plus Ib plus Ic, and it will be non-zero for an unbalanced system, and for balanced system it will be zero, and also it will be zero for if this is not connected and is not connected to ground. This point is G. This point is G. So these two things you should kept in mind. So here In will be equal to, for an unbalanced system, of course, Ia plus Ib plus Ic to be non-zero. So Ia will be equal to Ia1 plus Ia2 plus Ia0. Ib will be equal to A square times Ia1 plus Ia2 plus Ia0. Similarly, A times Ia1 plus A square times Ia2 plus Ia0. This is Ic. So Ia1 is to be we'll take to common here. You can say Ia1 is here, is E square Ia1 and Ai1. I have taken them to common, and here we have 1 plus A square plus A. It comes out to be equal to 0. Similarly, Ia2 here it is 1 is here, Ia2 it's A is here, and Ia2 it's A square is here. This also comes out to be equal to 0. Here we have Ia0 and Ia0. This comes out to be 3 times Ia0. You can see it from here. This In will be equal to 3 times Ia0. For an unbalanced system with neutral grounded, this In will be simply equal to 0 sequence component, 3 times to the 0 sequence component of the current. We have calculated it before. In that case, we have calculated this I0 in terms of Ia plus Ib plus Ic divided by 3. Here that is equal to In, so In will be equal to 3 times the 0 sequence component of the current. Now, here one more point is important. Since In will be 0 when neutral is not connected to ground, in that case this Ia0 will also be equal to 0. This Ia0 will always be present when neutral is connected to ground. Please keep this in mind. Now from here we need to calculate this Vn, that is voltage of this with respect to ground. It will be equal to simply voltage drop of this across this impedance due to this current In. Since the direction of the In is from this point to this point, you will see this point will be negative, this point will be positive. That means the voltage will be equal to minus In into Zn. That's what I have written over here. It's actually capital N, it's not small n. Minus In Zn, it comes out to be, when In is equal to 3 times Ia0, it is equal to minus 3 times Ia0 Zn with respect to ground. This is very important, the neutral voltage. So here important point I will repeat, I have told it before. There is no positive and negative sequence component of current, that is no voltage due to them present in the neutral voltage. Neutral voltage is only dependent upon the zero sequence component of the current. It is independent of the positive and negative sequence component of the current. So let's come to the sequence networks and equations, because finally we have to come to this sequence, how to represent some system in terms of sequence networks and sequence equations. That's very important. This is a transmission line, simple transmission line. We have 3 phases. This is phase A, phase B, phase C. Here the current IA, IB, IC. The voltage of this phase with respect to ground VA, and with respect to this VB and VC. It is self inductance of this line is XS. This XS almost you can see same. So they are very close to each other. They will definitely have mutual impedance, and we say that they are symmetrically placed so that they have the same mutual inductance. Between A and B is XM, B and C is XM, and C and A is XM. So XS is the self reactance of each line, XM is the mutual reactance between the two lines. Now the voltage drop between these two, VA and V dash, these 2 points will be equal to this multiplied by this, and the voltage drop of the mutual impedances. So we can write it as VA minus VA dash is equal to J times excess IA, that is the voltage drop in the self-inductance and voltage drop in the mutual inductance due to other currents. So this will be J times XM into IB, that is the mutual inductance between this line and this line, and current will be, of course, because of the other which is close to it, that is IB in this case. So XM, the third one is the mutual inductance voltage drop, that is this multiplied with this current, that is this. Similarly, VB minus VB dash will be like this, and VC minus VC dash will be like this. It's very simple, and I hope you understood this. So in terms of matrix form, I can write it as VA minus VA dash, VB minus VB dash, that is this, J into XS, XM, XM, this XS, this XM, this XM, this whole J will take now, XM, XS, XS. Similarly, this matrix will be like this. And then I will make another column matrix of IA, IB, and IC, because IA, IB, and IC in all the matrix. So it will be like this. So I can write it. This will be delta VABC. This will be Z, including this J. This will be IABC. So I can write it like this. This I have shown it again here. This is delta VABC matrix. This is Z matrix, including J. This is IABC. Let's say this equation first. So we can write it IABC is equal to IA, IB, IC in terms of sequence components. 1, 1, 1, 1, 1, A square A is this, IA naught, IA1, IA naught, which we have discussed earlier. Let us call this matrix as IA, IABC, this matrix as A, and this matrix is IA01 to sequence components. So that means IABC, the actual current in terms of sequence components, is related to each other by A. That means sequence components of current and actual current in three phases are related by this matrix A. That matrix A is given by this. So similarly, now this delta VABC, I will replace this IABC by this equation. So this delta VABC will be equal to Z, that is this Z, and this IABC will be A times IA012, that is A times IA012. This is, let's say, equation 3. Since we have represented this IABC in terms of, we can say, actual value of the currents in terms of sequence currents, we can represent the actual value of the voltage in terms of sequence voltages. So I can write it as VABC is equal to A, this also matrix, A into VA012. Similarly, delta VABC will be equal to A times delta VA012. So I'll put this equation into this. So that's why I have written, I put equation 4 into 3. When I put it over here, it comes out to be A into delta VA012, because delta VA012 is in place of this delta VABC. So delta VABC is replaced by this. So this equation will be A into delta V0, delta VA012 into Z A IA012. That equation is written over here. So I will take this A, or I will pre-multiply by A inverse to this. This A inverse into A will be equal to 1. That's identity matrix, that will be equal to 1, and this will be then unchanged. And when we pre-multiply this to this A inverse, it comes out to be A inverse Z into A, and this will be equal to this IA012. So this value A inverse, I have told you earlier, this will be equal to 1 by 3 1 A 1, this 1 1 A square A, which we have calculated earlier, not in this manner but in other way, and I told you that this will be the inverse of this. The only difference between this and this is that it is multiplied by 1 by 3, and this matrix, we can say it is the transpose of this matrix. Transpose, we cannot say it's transpose. Here it is first A and A square, here it is A square A, then A square, here A square A, here it is A and A square. So when we multiply these three matrices, I have not done it here, you can do it on your own, it comes out to be equal to J times XS plus twice XM. Wait a minute. Yes, this is right. Yes, this is right. Where is this? Yes, J times XS plus 2 times XM. These two columns will be, these two values will be 0. These two values will be 0. This xs minus xm, this will be 0, this will be 0, this is xs minus xm. This will be a diagonal matrix whose diagonal values are, first one is xs plus twice xm, second one is xs minus xm, and third one is xs minus xm. Now I will put this in this equation. So this will be delta VA naught, delta VA1, delta VA2. This will be xj xs plus 2s xm 0 0 xs minus xm, this is 0 0 0 xs, or z naught 0 0 0 z1 0 0 0 z2. This will be ia naught, ia1 and ia2. So you can see that this delta VA naught, if I get the actual equation, it will be equal to ia naught into z naught. Delta VA naught will be equal to ia1 into z1. Delta VA2 will be equal to ia2 into z2. You will see that, or here I will first write it as dot naught is equal to j times xs plus x2m, that is zero sequence impedance. Z1 is equal to j times xs minus xm, that is positive sequence impedance, and Z2 is equal to xs minus x0, that is negative sequence impedance. Because you will see that VA1 by, sorry, delta VA naught by IA naught will be equal to Z naught, delta VA1 divided by IA1 will be equal to Z1, delta VA2 divided by IA2 will be equal to Z2. You will see uh, there will be no other interference between the two. I can say that this delta VA1, delta VA naught will be simply equal to, I will repeat it, IA naught into Z naught. There is no term of IA1, IA2, Z1, Z2. This is very important. It represents the decoupledness of the system that I have told you earlier. You can see from earlier equations, which we have written like this, we have all the matrices full. We have the mutual inductance present. We have the mutual effect present. But here there is no mutual effect. You can see between 0 and 1, between 0 and 2, 0, between 1 and 0 and this 1 and 2, 0, between 1 and, sorry, 2 and 0 and 2 and 1, this is 0. There is no mutual interference between the sequence networks. That is why this is very important too. So for transmission line, positive and negative sequence impedance are equal. You can see from here xs minus xm, xs minus xm. Zero sequence impedance are much larger than the Z1 and Z2. That is around 2.5 times. You can see it from here. Since it is plus something and here is minus, it will be very larger than this. We can write it in equation Z1 is equal to Z2, which are less than that of Z0 in case of transmission line. The sequence circuit equations are decoupled from each other, that is there is no mutual sequence impedance, which I have told earlier. This is very important. So I hope this is very clear to you. Thank you very much.